Okay, so this week we're going to start to look at trig functions from a little bit different perspective. We're going to look at drawing them. Okay, and I showed you guys some different examples. And we'll do transformations. Okay, we'll stretch them, compress them, shift them up, down, left, and right. All right, so first thing I want to mention, and this is true for all trig functions, is they are periodic. And what periodic means is that the function repeats itself. You have to go a certain amount of degrees on the x-axis. And once you do that, you're just going to keep repeating the same y values over and over. So all different y values that you can get are going to start to repeat after a certain interval of x values. Now, that interval of x values, if you don't change sine or cosine, you don't do anything to it, just graph the very basic function, has a certain value. We've seen it before. Does anybody know how many degrees you'd have to go through on the sine or cosine function to go through every different value you could possibly have and get back to where you started and repeat? Anyone have a guess? Yeah. Yeah, it's 360 degrees. Okay? So we might have looked at this before, but if you take switch to degrees. If you take the sine of, say, 10 degrees, and you take the sine of 370, they come out exactly the same. That's because sine repeats every 360 degrees. All right. And I think we mentioned that at the end of a section at one point. It's called the periodic property for sine and cosine. Now, what would that be in radians? 360 degrees or 2 pi? Okay, so the length of that interval, that 2 pi, or 360 degrees, if you say it in degrees, that's called the period of the function. Okay, so the period is the length on the x-axis you have to go through before the y values repeat. And the length of this period, 2 pi, that's not only the period for sine and cosine, it's also the period for cosecant and secant. They also repeat every 2 pi. Tangent and cotangent are a little different. We looked at a graph of them really quick just so you could see them. They do repeat, but it's not every 2 pi. Tangent and cotangent naturally repeat a little faster than that. They repeat pi at 180 degrees. So if you took the tangent of 10 and then the tangent of 190, those would be the same. Okay, so it repeats every 180. Okay, but we'll look at that on Thursday. Okay. Another name for a period, we don't use the term as much, but it's called a cycle. And that term is used quite a bit, especially when you're measuring what's called cycles per second. Does anybody know where you measure cycles per second of something? Mm-hmm.
Would it be when something's oscillating, which is kind of a DE thing, power circuitry, we use it to time study.
Okay, this is used to measure something oscillating. It could be used to measure maybe lots of different things oscillating. I'm thinking of something in particular connected with what Ali was saying, electricity. Anybody think of where you measure something with electricity in cycles per second? AC current. Yeah, what about AC current? What does that have to do with how many cycles per second? Switches from positive to negative how many times per second? Do you know how many times? Alternating current switches back and forth 60 times per second. And cycles per second, it's named after someone, hertz. Okay? 60 hertz. So that is a term that's used. We don't use it as much. Okay? But alternating current oscillates 60 times per second. And if you have a multimeter or the right device, you can hook it up to an outlet and you can see the sine wave of the electrical current. Yep, use an oscilloscope. If you have like a generator or something that's making electricity, some generators, they don't make as like clean of electricity as like what you get from like the line off the street, like from the grid. But you can look at the curve of it, and it's not quite as smooth of a curve. Sometimes it could actually look more like this. Okay, it could kind of have this blocky pattern to it, rather than a nice smooth curve. And that just means it's not gonna be as good of an electricity for your device. If you're lighting a light bulb or something like that, it won't really matter. If you're running a motor, what could happen if this electricity isn't exactly at 60 hertz, it might run a little hot. Okay, it might overheat a little bit. But in general, things that aren't motors, things without sensitive electronics, they don't care as much. Any kind of charger you have, if you look at it, it has this number on it somewhere, 60, but it might say 60, or actually it might say it like this, 50/60 hertz. Anybody know why it might say 50 and 60? Because we don't use 50 at all. Anybody know where you use 50 hertz?
Commercial buildings?
What's that?
Commercial buildings?
I know some commercial buildings use different kind of electricity because they I know wood shops and stuff, they have what's called three-phase current or electricity. That's a little different. But where the 50 hertz is used in other countries, okay, like Europe, they use a 50 hertz system. So if you look at your transformer, your charger for your Chromebook, any of that stuff,
Australia.
a lot of it probably says 50/60 hertz.
Would they use it in Australia?
They might, I don't know. I haven't been there, so I haven't looked that one up. Yeah. Okay, so some of the things we're studying are definitely used in other fields. Okay, but we're going to stick with using the term period, usually more than a cycle. Yeah.
In welding for alternating current, sometimes they use square wave machines where the wave looks kind of blocky like that.
Yeah.
And it just makes it so that the arc that you're using is more precise because it goes down faster.
Okay, yep, so I didn't know that. That's interesting. And they have all kinds of variations. If you look at the electricity graph for any AC outlet in this room, it should look like that. But you can have it be very blocky, okay, which would be something like this. Or you can also have it not quite as blocky. So here's your curve. You could have more steps in the blockiness. So you could have something like that. So now what that's doing is it's approximating a sine wave a little closer than this first one. This is very, very blocky. This one's blocky, but it's got more steps in it. Okay, so different devices might operate a little differently. All right. But that's why sometimes on generators, things don't run quite the same as when they're on regular electricity. Unless you have a really expensive generator, then it might. Okay, a couple things that nobody mentioned when I showed the graphs is that sine is symmetric about the origin. Okay, so if I graph, let's just graph sine again. And if you don't do the right zoom, that's how your trig function will look. Okay? I've got to do zoom 7, and now it'll look the way it should. It's because I didn't have a good window. Right? And it's symmetric about the origin. Okay? Which basically means it's almost like reflecting it on a diagonal. this point here ends up down here. This point ends up down there. Okay? So that's what symmetric over the origin means. It's kind of like if you drew a diagonal line right through it. Each point, like this point right here, ends up right there. Okay, so that's symmetric over the origin. And cosine isn't symmetric over the origin, but it is symmetric over the y-axis. So if I graph that one, what that means is if you just mirror imaged it or just flipped it left to right, it would land right on top of itself. Okay, so any questions on that? So these graphs, they definitely have some symmetry to them. Okay, whenever we want to graph a sine or a cosine function, okay, we're not going to graph the wave forever. What I'm going to have you do is just graph one cycle or one period of the function. Okay, we always want to remember that this function does continue forever, left and right. Okay, but we're not sketching it forever. Okay, we're just going to graph one period of the function. Okay, and in order to do that, we really need 5 points. Okay, I like to find where it crosses the x-axis. So for the first period or the first cycle of the sine wave, that occurs at 0, pi, and 2 pi. And then if we can find the highest and the lowest value, we're pretty much set to graph it. Okay, so we try to find those 5 points. And those are the 5 points we're always going to graph. No matter how we transform it, we're going to figure out where these 5 points go. And that's it. Just those 5 points. You know, there's tons of other points if you keep graphing it forever. But every point on the graph is going to move exactly in the same direction. So all I need you to find is these first 5. Okay? And that'll give me one cycle of the graph. Also, if you look at them, look at those values. You've got pi over 2, pi, 3 pi over 2, 2 pi. Those are all spaced 90 degrees apart. 0, 90, 180, 270, 360. Whenever you graph your points, all the x's should be nicely spaced. Okay? Just like that, all equally spaced apart. Now, until we stretch and compress the graph horizontally, they're always going to be 90 degrees apart. Okay? If you shift it up, the spacing on the x-axis isn't affected. If you shift left or right, the spacing isn't affected because you're just moving the graph. Okay? If you do something like that, it doesn't affect the stretching or compressing horizontally. Okay, so for now, everything should be spaced 90 degrees apart. But it might not always start at 0. Okay, if you shift this graph to the right, it might start at pi, or 3 pi over 2. Or if you shift it to the left, it might start in the negatives. Okay, we'll take a look when we get to it. Okay, so anytime you want to do a transformation, okay, the most important thing you have to know is where the graph would be if you didn't do the transformation. Where would it start? If we can't figure out where the graph is starting, we're not going to be able to figure out where it's going to move to. So basically, I'm just going to put these 5 points in this graph in a table. Okay, so I've listed all my x values. 0, pi over 2, pi, 3 pi over 2, 2 pi. And now I want to just list out my y values. Okay, just by looking at that picture. Okay, so this is an accurate, pretty accurate picture. It's not perfect, but hopefully you get the idea. On the graph of y equals sine x, when x is 0, what's my y value? It's at 0. How about when I'm at pi over 2? I'm up at the highest it ever goes, which is 1. And then at pi, I'm back to 0. 3 pi over 2. And then 2 pi. Back to 0. And then it's going to repeat itself. So these are what I call the 5 starting points for the graph of sine. Okay, and we always use those 5. All right, so let's do the same thing for cosine. So when we graphed sine and cosine before, we saw that basically the only difference is one is shifted a little bit off from the other. Okay. Let's make the table, and then let's see if we can figure out what is the shift. How many degrees apart are sine and cosine? All right, so let's graph cosine. Okay, does everybody have the sine table? Okay, I'm just going to cover it up for a second. Now, when x is at 0, what's the y value this time? 1. How about when we're at pi over 2? 0. And then pi, we're at negative 1. Back to 0. Back to 1. Okay, so now you've got the table for sine and cosine. Anyone think they can tell me how many degrees off sine and cosine are? Yeah, they're 90 degrees off. Just connect the corresponding y values and look at when they occur. One occurs at 0. Okay, an x value of 0 gives you 1. An x value of pi over 2 gives you 1. So look at the difference between 0 and pi over 2. Okay, it's a difference of 90. Pi over 2 gives you a value of 0. Pi gives you a value of 0. What's the difference between pi and pi over 2? 90 again, or pi over 2. All right, so what that means is once we know how to shift things left and right, I could graph sine and cosine and make them look exactly the same. All I would have to do is take one of them and shift it 90 degrees, and you wouldn't be able to tell the difference on the calculator. Okay. So once we learn how to do a horizontal shift, we'll come back to that and see if we can figure out how to make sine and cosine look the same, at least on a graph. All right, so if we're only going to do one transformation at a time, then in these original tables, one column will stay the same, and one column will change. Which column changes and which column stays the same depends on the transformation you're doing. If you're going to shift up, that's going to change the y values. The x values will not change. If you were going to stretch or compress left and right, if you did something like this, if you stretch or compress left and right, notice there the y values aren't changing at all. Just take a particular point, focus on it. It's not moving up and down. Okay, so stretching and compressing left and right doesn't affect the y-axis. It only affects x. Okay, so as long as we're only doing one transformation at a time, this will always be true. And even on Wednesday, when we get into multiple transformations, we're still only going to do one at a time. Okay, we'll do the first one, and then we'll do the second one separate. Okay, but we always do one transformation at a time. Okay, now I'm going to talk specifically about the two transformations we're going to do today, which are these shifts. Okay, shifting left and right, and shifting up and down. Now, we've done this kind of transformation before. We've never called it this, and they usually don't call it this, unless you're dealing with a trig function. But all a phase shift is when the graph moves left and right. Not stretch left and right, just move left or right. It's like a translation. And let's take a look at like a function we've dealt with before. See if we remember how to move that left and right. And then we'll apply the same idea to sine and cosine. If I had the square root of x, and I want to move it 2 units to the right, how would I write that? How do you translate the graph square root x 2 units to the right? What is it? So can you tell me exactly what to write? And where is the minus 2? Inside. Yes. Okay. If you wanted to translate 2 units to the right, that's how you would do it. Square root x minus 2. Okay, so here's sine of x. How do you think I would translate that 2 units to the right? Yeah. That would translate the graph of sine 2 units to the right. Okay, it's exactly the same idea as every other function we've done all year. So a phase shift has the form of sine or cosine, and then you add or subtract a number inside the parentheses. Huge difference if you do it outside. That's totally different. And when I teach it in trig, this is the first time they've ever seen transformations, so they're not used to this idea that you have to do the opposite. But we've been doing that all year. So you should know that when you do minus a value inside, minus shifts to the right. And if you have plus, that'll shift left. Okay, that's same idea we've been doing all year. All right, so let's take a look at the graph of sine and cosine again and see if we can figure out how to do a phase shift and make one of them look like the other. So I already have cosine. Let me graph sine. So let's look at it from the perspective of the blue one. Okay, the blue one is cosine. How far off are sine and cosine? How many degrees did we say? 90 degrees off. So if you're looking at it from the perspective of cosine, which way would you have to shift cosine to turn it into sine? You'd have to shift it 90 degrees to the right. Okay? And then how do you shift something right? Plus 90 or minus 90? Minus 90. So if I graph cosine of x minus 90, sine and cosine should now look exactly the same. And they do. Okay, so that doesn't prove, but what it suggests is that sine and cosine are phase shifts of each other. And they really are. Okay, they are phase shifts of each other by 90 degrees. So what that means is anything you can graph with cosine, you could graph it with sine too. You just have to shift it a little bit. All right, so when we do a phase shift, we're moving left and right. Which values are affected when you move things left and right? Your x values or your y values? Your x's are going to be affected. They're going to change. Well, if the x's are the ones that are going to change, then the y's are the ones that are going to stay the same. So when we're trying to figure out where do these 5 points move to when we do a phase shift, these values, if you're doing sine, or these values, if you're doing cosine, are not affected. So what I just circled, copy those values down from the original table. They're going to go into our new table. Now, if the y's are going to stay the same, we got to figure out how do the x's change. Well, you look at your problem. Okay, like in the one we're going to graph in a second, it's x minus pi over 2. Determine what has been added or subtracted inside the parentheses. Okay, that's the argument. I've subtracted pi over 2. And we have to remember that inside the parentheses, you do the opposite. Okay. So we've subtracted pi over 2. We're going to do the opposite of that to all the x values. We're going to add pi over 2. And what that's going to do is cause everything to shift right. If you add a value to all the x's, it's going to push them all to the right, and that's exactly what should happen. Minus a number shifts everything to the right. Now there's 4 transformations we're going to study. 2 are rigid transformations. They're like translations, up, down, left, and right. And then 2 of them are non-rigid, okay? Stretching and compressing horizontally or vertically. The other way to think about them, out of the 4 transformations, there's 2 that you have to do the opposite, and there's 2 that you don't. Okay, so phase shift is one of the transformations that you do the opposite of what you see. If you see minus, you're going to do plus to all the x's. If you see plus, you're going to do minus. Okay, we're not going to see the other transformation that you do the opposite for until tomorrow. Okay. Just remember that. Phase shift, do the opposite. All right, so I already asked you what happens here. This is a phase shift. I know it's a phase shift because I'm subtracting, or I could be adding, in the parentheses. Has to be in the parentheses. This is not a phase shift. That's totally different. This, that's not a phase shift. Okay? To have a phase shift, the letter and what you're adding or subtracting have to be grouped together in the same parentheses. All right. So Josh, what column for a phase shift is going to stay the same? Y's. So I'm going to go back to my original table, and I'm going to copy down my y values for sine. Okay, Quinn, can you tell me my y values for sine?
0, 1, 0, -1, 0.
Okay. Those are my y's. And now I'm going to take all my x's, which, Andrew, can you give me my x values?
X, 0, pi over 2, pi, 3 pi over 2, 2 pi.
Yep. And take all these x values, and I'm going to do something to all of them. Allie, what am I going to do to every one of those?
Add pi over 2.
Yep, I'm going to add pi over 2. Now, when we do this, we don't write any decimals. We're going to leave everything in terms of pi. And on the test, what I'm going to be grading is this final table and the picture, which we'll do the picture in a second. Okay, so 0 plus pi over 2 is pi over 2. How about pi over 2 plus pi over 2? Yeah, it's 2 pi over 2, but the 2's cancel and you just get pi. Now, to add these up, what do I have to do first? Yeah? Yeah, I need the same denominator. So what is the common denominator between 1 and 2, Amanda? 2. So double the top, double the bottom. What's 2 pi over 2 plus 1 pi over 2? 3 pi over 2. Next one already has a common denominator. 3 pi over 2 plus 1 pi over 2. 2 pi. And now you can do the same thing again here. Find the common denominator. Or you can look for the pattern. If you tell me everything with a denominator of 2, the first one is 1 pi over 2. What would the second one be? 2 pi over 2. 3 pi over 2. 4 pi over 2. 5 pi over 2. So if you write everything with the same denominator, you'll see a nice pattern. I'd rather you reduce things, though, then leave it as 4 pi over 2. I'd rather you write it as 2 pi. What would the next one after 5 pi over 2 be? Yeah, 6 pi over 2, which is 3 pi. Then 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. We could keep going if we want equally spaced x values. But we stop with that. So that's where those 5 original points that I gave you shifted to. Bless you. Okay, the way I grade this, I give you 1 point for each x and y value you get right. So this table would be worth 10 points, okay, on the test. And then the graph itself is either worth 1 or 2 points, however the numbers work out. All right, so when I set up my graph, I'm not going to label it on the x-axis 1, 2, 3, 4, 5, 6, okay, because my values are pretty messy. As long as I label it and keep everything equally spaced, you can label it however you want. So I'm going to label it with these x values. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. And those are all equally spaced. That's 0, 90, 180, 270, 360, 450. Just plus 90 each time in degrees. Okay, the highest is 1, the lowest is -1. And if you don't label your axes when you graph it, but you still get the picture right, which we're about to do, I would take off a point. Okay, if you don't label anything, you're going to lose credit. So make sure you do label your x and y axis, unless you're going by ones. And technically, if you're going by ones, you don't have to label it. But most of the time on the x-axis, we don't. And sometimes on the y-axis, we don't either. Okay, so we have pi over 2, 0. Pi, we're at 1. 3 pi over 2 to 0. 2 pi, we're at -1. And 5 pi over 2, back to 0. Okay, remember, when you connect it, try to make it look curved. Okay, sine and cosine don't have any sharp turns in them. They should all look nice and curved. Okay, so that's the final graph. The new graph would have been more right there. It would have gone 0 to 2 pi. Okay, so we shifted it to the right. Okay, any questions on that? All right, so we'll try maybe 1 or 2 more phase shifts, and then we'll look at our last transformation, which is a lot easier arithmetic-wise, which is the vertical shift. Okay, but anytime you have to do a phase shift, you got to work with pi. So you got to get common denominators and all that stuff. Okay, how do I know that this is a phase shift? Besides, it's the only one we've learned so far. Yeah. Yeah, you're adding or subtracting in parentheses. So because it's a phase shift, about Jeff, which value is not affected by a phase shift?
Y.
The y's. So can you tell me my y values for cosine?
Pi. Oh, the y values?
Y values.
0, 1, -1.
So those are the right numbers, but we don't start with 0 for cosine.
Oh, 1, 0, -1, 0, 1.
Yep. So we just got to be careful, because if you accidentally copy the wrong column, which I've done before, you could be graphing sine x plus pi and not cosine x plus pi. So make sure we get the right y values. Now we take all the x values. And Quinn, what am I going to do to all my x values? Careful, that would shift it the wrong way. Yeah. Subtract pi. And there's a lot of ways you can do this. You can find common denominators. You could do the easy ones first. Negative pi. What's pi minus pi? And 2 pi minus 1 pi? 1 pi. And all the x's have to be equally spaced. So if everything's equally spaced, what's exactly equally spaced between 0 and pi? 1/2 pi. And what's equally spaced between negative pi and 0? Negative 1/2 pi. Or if you find common denominators, you'll get exactly the same answers. So basically what I did is I just averaged to find what was in the middle. And so you can do a trick like that if it speeds things up. Questions on the table? Okay, so make sure on the homework tonight that you show that table. Okay, if all you show is the final graph, you'll get half credit. Okay, I got to see that table, and that's what I'm going to really look for on the test. Okay, table's worth 10 points. All right, so if you're smart, sometimes you can put your labels in the right spot so you don't draw through them like I did here. If you draw through them, it's not a big deal. But let's see, I'm going to put negative pi over 2. 0, it's already really labeled. That's where the axis intersects, so we don't need it, but you can label it. Pi over 2 and pi. And the highest value is 1 and negative 1. Kind of hard to squeeze that one in. Maybe what I should have done here is put that label up above or move, I don't know, or something. All right. So negative pi, we're at 1. 0. 0, negative 1. Pi over 2, 0. Pi, 1. Now, this is the graph that a lot of people draw it. They just draw it like this. Remember, it's not an absolute value function. Okay? It's part of a wave, and that's kind of the middle section of the wave. So it would kind of, come down, hit the bottom here, come up, hit the top, and that's how you would sketch it. And then it would continue on. Okay, any questions on that one? All right, so the last one we're going to do is a phase shift. I want to look at this one, not really for the arithmetic, but when you set up your axes. Because some people make a mistake on this. Okay, so what I'm going to do is I'll do the x and the y values quickly, just so we can get to the graph. Here's my y's. Now I'm going to take all my x's. And what am I going to do to all of them? I'm going to subtract pi over 4. Okay, all the way down. Okay, and if you find common denominators, what you're going to get is negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And the pattern there is basically odd numbers in the numerator. Okay, but you can go ahead and find your common denominators, and it'll work out. All right, now let's graph it. I'm going to put negative pi over 4 right there. How much is that in degrees? Negative pi over 4. How much? That's negative 45 degrees. So how much did I just make this gap worth? I just made that gap worth 45. Okay? So now, where would I put pi over 4? Yeah, don't put it at the origin, right? Because the origin is 0. Put it at the next one. Now, here's the important thing. Where would I put 3 pi over 4? I have to skip one, okay? Because I skipped one for the origin. right? Each gap is worth 45. 3 pi over 4 is 2 gaps away from pi over 4. Here's pi over 4, 2 pi over 4, 3 pi over 4. 4 pi over 4, 5 pi over 4. 6 pi over 4, 7 pi over 4. Okay, that's the one where people mess up the spacing sometimes. But just be consistent. Okay, if you have to, convert those to degrees temporarily and just make sure everything is equally spaced. Negative 45, 45, 135, 225, 315. Okay, don't do something that's equivalent to this on your x-axis. You can't start by going by ones or some scale, and then all of a sudden in the middle change your scale, and then go back to your scale. You have to be consistent the whole time. Okay, and then any questions on how you'd graph that? You just take the points in the table and just graph them. Okay, but I just wanted to make sure everybody understands what we just did there. Any questions on setting up the x-axis? All right. So that's the harder transformation for today because you have to work with common denominators and pi. Vertical shift is a lot easier because now we're going to be working with the y column. And think of the numbers you have in the y column. It's all ones and zeros, negative ones. Okay? Arithmetic with ones and zeros and negative ones, a lot easier than arithmetic with fractions that have pi. So vertical shift, this is going to translate your graph up or down. Okay? And it has the form y equals sine of x or cosine of x. And it can be plus or minus a number. But what's different about the adding and subtracting now? It's on the outside. Okay? So this is a vertical shift. This is also a vertical shift. I don't know why you do that, but you could. This is also a vertical shift. Okay? Because some people say, oh, it's not in parentheses. Well, all of these now have parentheses. Well, the second ones they did. But those are still vertical shifts. You've got to group the argument and the number you're adding in the same set of parentheses for it to be a phase shift. Okay, so any questions on the difference just between what a vertical shift and what a phase shift looks like? Now, what do you think sine of x plus 3 is going to do? It's a vertical shift, but is it going to shift it up 3 or down 3? Up 3. Yeah, it does. Vertical transformations, whether it's shifting or stretching, do exactly what you would expect. Horizontal transformations do the opposite. Okay, so if that helps you to remember, you could write that. Horizontal transformations are always the opposite. So let's graph the original in blue and sine of x plus 3 in red. Okay, we're just barely going to see it. It's going to be right on the edge of the top, but it doesn't go off the screen. Okay, well, that's it. That's a vertical shift. So plus the number moves up, minus the number moves down. Now, if you had a phase shift and a vertical shift in the same problem, okay, let's say I had you graph something like this, okay, which we will do on Wednesday. Do these transformations affect each other? Like which one you do first? What do you think? Okay, so there is a certain order we're going to stick with. That will always be the correct order. But do you think it would matter which one you do first? Why not? Sometimes when you have multiple transformations, it does. And the reason it does, just think of PEMDAS. Like, if you double a number and then add 5, or add 5 and then double, it's very different. Okay? Just same thing here. Sometimes it matters, sometimes it doesn't. In this case, it wouldn't really matter. How come?
Because the one inside the parentheses affects the x values, and the one outside the parentheses affects the y values.
Right? If you have multiple transformations and you only have one transformation affecting the x's and one affecting the y's, those are totally separate. The only time multiple transformations gets tricky is when you have two transformations affecting the same axis, like shifting it right and then stretching or compressing horizontally. Then you have to do it in a certain order. But technically, you don't have to do this one in a certain order, but I'll give you the order you should follow. And then if you follow it, then you don't have to guess, should I follow the order or not? Just, we'll always stick with it, and then you'll always be okay. Right? But yep, that's what I was looking for. All right, so to find where the 5 original points are going to go for a vertical shift, this time your x's are going to stay the same. So those 0, pi over 2, pi, 3 pi over 2, and 2 pi, what I just said is going to be the answer to your x's in every problem with a vertical shift. They are not going to change. And then to find the new y values, you just add or subtract d, or d, to all the original y values. Okay, don't do the opposite for this one. That's, yep. A lot of people do the opposite for a vertical shift. I think they just get in the habit if that's what you do for a phase shift. But it's not what you do here. So don't do the opposite. Okay, so usually the vertical transformations, those are the easiest ones. When we do stretching vertically, it's super easy because you're working with the y's. When we get into stretching or compressing horizontally, a little harder because we got to go back to working with the x's. Okay, but we won't do the other two till tomorrow. All right, so let's try graphing cosine x plus 2. All right, first, who can tell me what kind of transformation that is? And then explain to me how you know. So your two choices are phase shift or vertical shift. Unless you think I'm asking you a question about something I didn't teach you, then it could be something else. Yeah. That is vertical shift, yeah. And how do you know it's a vertical shift and not a phase shift?
Because it's not parentheses.
What if I did this?
Because, oh, there's no are in parentheses, like the adding and subtracting in parentheses.
Yeah, the x, the plus or minus sign, and the number are not all together in a set of parentheses. So here's a vertical shift. And Rachel, for a vertical shift, what column stays the same? The x's. Okay, when you shift vertically, that affects the y-axis. So how about Pacey? Can you tell me what are my x values for cosine? Actually, for sine too, they're the same.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Those are my x values. And my y values, take all the originals. Make sure you get them from the cosine table, not from the sine table. And Tom, what am I going to do to all those y values? I'm going to add 2 to all of them. Can you tell me what I would get when I do that for my final answers?
3, 2, 1, 2, 3.
Yeah. Okay. So there's our vertical shift. Shift it up 2. So let's graph it. I'm going to label my x-axis like this. Just pick values that are equally spaced, and it's pretty easy if you just pick the values that are in your table. Right, and I'm going to go by ones. 1, 2, 3 on the y-axis. So we've got 0, 3. Pi over 2, we're at 2. Pi, we're at 1. 3 pi over 2, back to 2, and 2 pi, back at 3. For the worksheets that I give you, you already have grid lines on them, so...
You put pi at 0, so pi.
Oh, thank you. So I put, wait, which one did I do? Pi over 2.
You put pi at 0, is off.
Oh, yeah, it's off, yeah. Thank you. So when you have it, your grid lines, it'll make things a little easier to keep track of. All right, so let's sketch this. And one thing you can remember when you're sketching, something special happens at this point and this point on the curve. Does anybody recognize what happens there? Or what should be happening? Look at the direction of the curve itself. What direction is this part of the curve going in? Yeah? It's curving down. What's happening in here? It's curving up. And then what's happening here? It's curving down again. So what's happening at this point and this point is a change in the curvature. Okay? In calculus, we call that a point of inflection. Okay? It's a point at which the curvature of the graph changes. And using what's called a derivative, we could find points of inflection in any graph. Okay? But that might help you, not in terms of the name, but just if you think in your head, oh, when I sketch it, the curvature should switch there. So if you start drawing a V shape, your curvature wouldn't switch. Okay? And a lot of times what they call curvature is concavity. Okay? In this first section, it's concave down. In the middle section, it's concave up. And then it goes back to concave down. Okay, so any questions on sketching that one? Okay, any questions on how you'd sketch sine of x minus 3? Just take your y values for sine and subtract 3 from all of them. Okay, it would be just as straightforward as the last one. Okay, so the homework tonight, it will be a worksheet. Okay, it'll be these 7 problems, so I'll just pass them out. They're already on the worksheet. We'll take a look at it tomorrow, and then we'll finish up all the individual transformations of sine and cosine. And then Wednesday, we'll start putting it together and do multiple. Oh, also, my extra help this week, I think we'll keep it Thursday, okay, because the test will be a take-home due Friday.